Watch a dot race along a curve that loops back on itself, goes straight up, even crosses its own path. A normal function y equals f of x can't describe that, so how do we capture motion this free? The answer is parametric equations, and once you attach a velocity vector to that moving point, every exam question about speed, direction, and distance falls right out. Let's see it. This is full marks. Today, parametric curves and motion, how a particle moves, how fast and how far, then 2 real AP exam problems. Here's the idea. Instead of giving y in terms of x, we let a third variable, time t, drive both. We give x of t and y of t separately. As t advances, the point at x of t, y of t traces out a path, and it can loop, double back, or go vertical, things a normal function never could. What's the slope of that path? It's the rate y changes divided by the rate x changes. Dy dx equals dy dt over dx dt, the two time derivatives divided. That ratio gives the direction the curve is heading at any instant. Now make it physical. The horizontal velocity is x prime of t, the vertical velocity is y prime of t. Attach two arrows to the moving point, one pointing across, one pointing up, and watch them stretch and shrink as the particle speeds up and slows down. Add those two arrows tip to tail and you get the velocity vector. It always points along the path it's tangent to the curve, and it tells you the exact direction the particle is moving at that moment. Speed is different from velocity. Speed is just how fast, ignoring direction. It's the length of the velocity vector. By the Pythagorean theorem on the two components, speed equals the square root of x prime squared plus y prime squared. And total distance traveled? Add up speed times a tiny slice of time all along the trip. That's an integral. The total distance is the integral of the speed, the square root of x prime squared plus y prime squared dt. It's literally the arc length of the path. Careful, distance is not displacement. Distance is the full length of the path traveled, and it only grows. Displacement is just the straight line from start to finish. The exam loves to test whether you know the difference. Exercise 1, a real AP question. A particle has position x of t equals 6t over t plus 1 and y of t equals negative 8 over t squared plus 4. Find the slope of the tangent to its path at t equals 2. Use dy dx equals dy dt over dx dt. First, x prime of t by the quotient rule, that's 6 over t plus 1 squared. At t equals 2, that's 6 over 9, which is 2/3. Now y prime of t by the chain rule, that's 16t over t squared plus 4 squared. At t equals 2, that's 32 over 64 1/2. So the slope is 1/2 divided by 2/3, which is 3/4. That's answer C. Exercise 2, also real, and this one's calculator active. A particle's velocity vector is 4e to the minus t, comma, sine of 1 plus root t. Find the total distance it travels from t equals 1 to t equals 3. Total distance is the integral of the speed. So set up the integral from 1 to 3 of the square root of 4e to the minus t squared plus sine of 1 plus root t squared dt. Notice the integrand is exactly the speed, the length of the velocity vector. This integral has no clean closed form, so on a calculator active question you just evaluate it. The result is about 1.861. That's answer A. Set up the speed integral, then let the calculator finish. Recap: parametric equations let x of t and y of t trace any path. The slope is dy dt over dx dt. The velocity vector is x prime, y prime, tangent to the path, pointing the way you move. Speed is its length, the square root of x prime squared plus y prime squared. And total distance is the integral of that speed over time. We can now describe any motion in the plane. Next, one of the most beautiful ideas in all of calculus, building any curve out of simple powers with Taylor series and finding exactly where that magic stops working. That's next on Full Marks.